discussed on C++, bit of review on C's, and then we start discussing what's on the textbook, more of a performances, how we measure a performances, and probably in two different aspects. We start looking at it as in what? Space and time complexity. 그죠? Yeah. Yes, I know. I wanted to just do a review and quickly come over. Just because we have a camera, I'm gonna go really fast and then go to that time complexity. So how is it determined? Bit of review, programming performances, amount of time and memory needed for the run the program, analytical, experimental that we discovered, we discussed last week. Space, amount of memory program occupies, basically those variables. The easiest thing that you can first look at is when you declare your variables in the beginning of your program, those things have their own space. So those first thing that you can easily determine before you even run the program, right? Well, what is it? Integer 4 byte, something like that, those stuff. It's quite easy to do. Time, we start discussing the time. One of the easiest thing is number of executions, number of steps. How many lines of code that you have might be easy things to start from. And then we briefly look at it last class as single line, how many times a single line is being called again. So those are frequency issues that we're gonna discuss. Briefly looked at it. So we didn't care too much about the space complexity at this point, but you should know what was the important stuff of what was the things to look at for saving the space complexity, assuming that you're writing your own programs. Well, yeah, compile option, one of the first thing, or the variables that we discussed. Those few things that you can actually manipulate and you can change your program. What did I say about those compiler options? What you could change your you could give or extract some of the compiler options, then you can make your program smaller. When you actually including those debugging options in your C or C++ compilers, then typically your program gets really large, but it's unnecessary at some point. So those things that you can play with, and the space complexity may define an upper bound of the data the program can handle. Stuff like that we discussed last week. Instruction spaces. Program space is combination of instruction space plus data space, and stack was what? When we're discussing the stack space, even though we didn't cover the stack data structures yet, but what was it again? Stack space is related to what? Well, when they start talking about the stack space, they're actually referring to a function calls. How many times you call a function that depends on the stack space can grow. So it changes how much space it requires. And then I think one of the final questions on this regarding the stack space was, what about recursive function calls? Is it preferable in the aspect of space complexity? What was it? No, right? It grows a lot. So that was a quick review on the stuff that we did last week. Hopefully those part I also ask you guys to read for the textbook, those answers why recursive function is not. Well, you have to, at some point you have to use it, but in terms of space complexity, why it's not preferable. Answers are in the textbook. Do we have all our textbook yet? 산 사람, raise your hand. If you buy those. Okay. Again, you guys buying your textbook is nothing to do with me. I don't get any money out of this textbook. 그죠? 오해하지 마요, 혹시나. 난 뭐 돈 하나 내 책 아니니까 it's not my stuff. But you will need your textbooks for some of the explanation, and some of the slide will referring to those textbooks. Okay, data space quickly looked at, and data space a matrix like array like. We simply multiply by the size of variables, and then whether it's a 2D, 1D, you can actually determine. Yeah? What else? Stack we discussed. What is the impact of recursive functions? I explained this. Space complexity summary, given what you know, space complexity, what can you do differently, make your program more space efficiently. I don't think I'm gonna ask you this in the exam. This has nothing to do with the exam part, but just for your general knowledge when you're doing your programming, I mentioned a few times, it's important, it's about your habits. When you're doing your programming, make it, remove some of the unnecessary variable declarations or play with those compiler options. Those are habits. If you have those stuff from the beginning, then it will be better later. Anybody read or understand 2.2.2 examples? Anybody even start flipping your pages? Monday morning, 9 o'clock, no one's awake. You know? I actually admire that you guys in the class. It's not too bad. Imagine. I also checked the EGF this morning. We have 46 people registered in. I don't think that's correct. 그죠? 오늘? That's what I thought too. I was expecting to see more than 60. So we'll see how it goes. Time complexity, we start looking at it. We stop around here, right? Stop around here. Time complexity. Time complexity is amount of computer time a program needs to run. But we all know, because we cover some of the pseudocode ideas, abstractions, that same program in your computer, it takes 10 seconds, the other one's computer is 20 seconds. It doesn't mean that your algorithm is better than the others. It's the same program, right? It depends on the hardware and your memory configurations. But this way, you can actually compare two different programs in actually pencil and papers. Write it down, analytical, and see which one is faster. That was the basis of when you try to compare which one is better algorithm than the other. 그죠? Time, why do we care about time complexity? Like I say, some computers requires upper time, upper bound. They like to know in worst time cases. Usually upper means the worst case that we know. Sure, the first years know the worst time cases. If, for example, loop n goes infinity, those stuff. I mean, you assume the extremes and then see what might be the maximum requirements that your computer need to have to run a certain program or algorithms. Some programs require a real-time responses, so they like to run it really fast. If they have many solutions to a problem, typically we like to choose the quickest or optimal. That's why we study this, comparing the time complexity, the performances of the algorithms. How do we measure? Count a particular operations, operation count, or count the number of steps. Asymptotic complexity, big O's. I'm going really fast because I assume that everyone knows this from your previous courses. 그죠? Right? Big O's, no n square, log n, no responses. 아, 진짜 짜증나. And then I brought up this, and I wanted to show you some animation on insertion sort. I don't care about the algorithm itself. There are thousands of different, not thousands, but there are a couple of different ways of implementing this insertion sort. So I don't care whether you understand the algorithm itself or not. But here's how this looked like. So it was just comparing, you have a series of numbers, start comparing from the beginning. If you go to the next one, you see that your number is bigger than the second one, then you switch the place. Or is it the other way around? So you keep forwarding until you find the right place. And then you start from the second one and move to the front again and start comparing. So beginning from the first element, not first one. So the first one should be 0, 0, 1, 2, 3. So, and then they put their numbers in. Every time they advanced, they compare. And then if they match the condition, they switch the place. I hope we have that animation coming. So what we're going to look at under this algorithm is the first one is to look at is how much comparison they will do. The t current number at the index is comparing to the next one, I think. And then whether they satisfy the condition. So every time I have to satisfy this, while 0 is bigger than a greater than 0, greater or equal to 0, and this is smaller, t is smaller than the next one, then I should replace those conditions. That's why, so we're going to count that how many times does it doing the comparisons. So it depends on, it all depends on the n. N is certain number, arbitrary numbers that you want to pick out. If there is a 10 elements, so n will be 10. Pick an instance characteristics of n. N is the number of elements in the case of insertion sort. Determine the count as a function of this instance characteristic. Basically, let's count how many times those comparisons will be done. Same thing. We already seen the answers of this algorithm, right? Last class. We have steps, and then we already know how many times those function calls will be called in it. So basically questions like this, same thing. How many comparisons are made? Number of comparisons depends on the elements in the list and the current value, as well as on the n. So we're going to see how that comes out. What might be the worst case of this thing?
Comparing one number to the entire.
Yeah, so you will do a maximum comparison. Minimum case. Not minimum, yeah, best case. Worst case, best case. Best case, obviously, the minimum comparison, if that's possible. Average count. Average count is a bit more than this. I mean, average, if you just simply add maximum plus minimum divided by 2, I don't know, it gives you a average. But later, the average count is a bit more complex concept. So we'll see. I don't think we're going to cover the average value later, but we'll see. So in this case, for I, j, blah, blah, blah. If A is 1, 2, 3, 4, T is 0, the value is comparing. T is 0. 0, 1. 0 is less than 1, 0 is less than 2, 0 is less than 3, 0 is less than 4. That's 4 comparison is being done. Likewise, if it's I, that is I comparison for single time, single insertion, they try to do. 그죠? Simple as this. So later, we're going to slightly change this number to this i's, n's, or other variables that, so we can explain this more theoretically. So bottom line is like this. So if you do a double loop, first one, try to insert, compare, and then second one, it goes to the second in the list. So it goes like this, n plus n minus 1 times. This is how many comparisons we'll do. This is how you add these numbers up, right? This is number of total comparison for this particular case. But we all know, as simple as this is n squared. The maximum will be n squared. We just simply discard some of the n values later. Linear factors would not be will not have too much influences if n goes really big. So that's how you look at this type of stuff. Insertion sort. If you looked it up, the insertion sort algorithms from the internet, they have different implementations. That's why I actually try to show you 2 different algorithms. So the number of comparisons might be slightly different, depends on your implementation. So those are examples on the textbook. If I'm speaking too fast or I'm going too fast, you can still read your examples from the textbook. All I want you to know is just know the rough upper bound. I mean, forget about this stuff. number of comparisons. But I just see a 2 for loops inside, so I can guess the worst bound is n squared. So you have to compare every single stuff to the every other pairs. So n times n minus 1. Step count, operation count, omits accounting for the time spent all but choosing operation, step count, methods count for all time spent all part of the program. How long does to finish this program, I guess? A program step is loosely defined. What do you mean loosely defined? To be a syntactically or semantically meaningful segments of the program for which execution time is depends on the instance of the characteristics. Program step is loosely defined. So depends on how you want to look at it. Some people just wanted to look at the main part of the algorithm. That's what determines the overall performance of the algorithm. So they just, maybe their number slightly less than the actual formal ones. So it doesn't really matter. That's why they say loosely defined. 100 adds, 100 subtractions, 1,000 multiplication can be counted as a one step. Depends on how you want to look at it. Maybe for us, 1,000 multiplication is single multiplication important to us, but some big programs, single multiplication is nothing. This 1,000 multiplication is maybe can be done in nanoseconds. Doesn't really matter for them. So they just count it as a one step. That's okay too. You don't have to count them as 1,000 steps. So that's why they have a different definition from place to place. Defined. Meaningful segment. What's a syntactically? What's a syntactically or semantically? Syntax. What is a syntax?
Syntax is a structure of a language.
Yeah, it's a grammar of the language. Single line. 문법. That's how we write your programs. It's semantically. Semantics. I mentioned this many times last year's Introduction to Computer Science. Semantics. What it means, it has 1,000 multiplication in it, so that means it's doing the 1,000 multiplication of a single line, at the single line. So, 문법이 되든, 뭐 문법을 중요시하든 하면 카운트가 좀 늘어날 거고, 이게 뭐 하는 거다라는 거로 넘어가면 카운트가 확 줄어들 거고, 뭐 그런 식으로 받아들이면 돼요. However, NS cannot be counted as one step. Here's how I take that statement. N can be too much. N can be infinity. If you want to count that as a single step, this doesn't make sense. 1,000 is okay, 100 is okay, but what if you're dealing with a million multiplications? It obviously takes much longer time than the other ones. So if you start using this n to describe the performance of the algorithm, maybe single step, too much. Even if it says so loosely defined. Okay. So this was the same algorithm we looked at, and this is steps. I mean, steps are quite easy to look at. Of course, these numbers can be different. I think your textbook has a slightly different interpretation too. It doesn't really matter for this. I mean, all I care at the bottom line is whether you can determine the big O's and small O's, omegas that we cover. So, like this steps, single line, I'm gonna call that as a one step. This one is almost empty, nothing, so I'm gonna call it as a 0. Comment is also 0. Declaration of a certain value, you actually put the number, certain number into t, so that counted as a single operation. This is just initialization of a certain value j, but you didn't give them a value, so I'm just gonna call it as a 0. This one line declaring for loops and defining and comparison conditions, that is a one step. Next one is switching the places. The other one is also, it's a part of the switching process too. 0. So this is a typical steps for execution. So how many steps do I need? 1, 2, 3, 4, 5. You just count the for loop as a single step. It's not meaningful to us. So the next step was just try to look at the frequencies. How many times a single step is being called? So that is first line, it goes, step 1 goes, and then you go through the loops inside, but it goes from I, from 1 to n, so that's n minus 1 times the single step will be called, n minus 1 frequencies. Likewise, whatever inside here doesn't include in the second loop, so they will be called at the same time as n minus 1. Once you're in the loop inside the loop, for loop, this is what we looked at from the last few slides ago, at 1 plus 2 plus 3 plus 4 plus. So n times n minus 1 divided by 2 is being done. I think this n minus 1 is outside, not in the within the loop. See the taps, there's no tap inside. Sorry for the confusions, but it should be okay. 맨 마지막 라인은 두 번째 룹 안에 들어간 게 아니라 바깥에요, 바깥에. That's why it says n minus 1. 이거 왜 n minus 1이야? It doesn't really matter. You can call it as a 0. I mean, that was the last bottom one. 이거 doesn't really matter. 0 is fine with me. So, if I ask you a question that what is a, how many steps, how many time steps does it require for this single algorithm to run? What can you do? Easy. I asked for the overall performance of this algorithms in terms of the steps. What do? Yeah, you add them all. You add this all. Add them all. You add them all. You have that 뭐야 저게? What do you call that? 방정식? N squared plus 3n minus 4. Okay. I have this. This is, I guess, the overall time steps for that particular algorithm can have. Again, no. Later, I might ask you some questions like finding an right n values, that boundary n values that the other algorithm will exceed the performance of this one. Or what is the boundary n values that stays better than the other algorithms, like that. So it's basically what 방정식. What year do you guys do this type of stuff? 방정식 몇 학년 때 배워요? 중학교? Maybe nowadays elementary. So, surprisingly later, probably midterm or finals, I usually ask a similar question to the exams, and I simply ask you to calculate the value of n given some numbers. Yeah, surprisingly, you guys can't even do any 방정식 anymore. 그럴 것 같지? 방정식 저기다 뭐 간판 하나 더 주고 n이 뭐가 되면 뭐가 되냐 이렇게 물어보면 생각보다 많은 사람이 방정식을 푸는 걸 다 까먹었어요. 웃지? It's probably one of you. So read 2.19, 2.22. This particular chapter will ask you to read many examples, but examples are really short, and it's not that much. And the other chapters will not ask you too much. I'm not going to ask you to read too many examples from the textbook, but these ones are short and hopefully try to make you understand. Read it. Asymptotic complexity. This is the key part. I like to use this more often. I mean, those formulas in the previous slide, it's just basically how you we like to tell you how we actually calculate those stuff. It's not, but those small numbers are not that important. -4, it's not meaningful for us. But this one is 2 important reasons to determine the operation and step counts. To compare the time complexity of the 2 programs that compute the same function that I mentioned. The bottom line of learning all this is just to try to compare 2 different algorithms or programs for their performances. And to predict the growth in the runtime as the instance characteristics changes. I mentioned a few times, n goes to infinity. It means n grows. N goes 10,000, 10,000, million, maybe billion. Then, depends on the n, we can predict how this algorithm will perform, how long it takes. How long it takes. That's why we usually draw that 2D graph, right? N square goes like this way, goes really fast after certain points. 그죠? Okay, actually, going back to that question. Previous formula that I mentioned, well, at some point I'm going to ask you to find the right n values. What does that mean? Let's say some functions x squared like this. I will ask you to find a point. It's a linear function here. What is a meeting point between two lines? 이거 뭐야 이거? Probably later I will give you a bit more complex. 큰일 났다. 이거 보자마자 와. No, it's actually I'm asking you these questions. Which point? This is algorithm 1. Let's say this is algorithm 2. Which point this algorithm will exceed algorithm 1? So that might be the n number, the value of n at this point. Okay. Neither of these two yield a very accurate measures. Operation count focus on key operations and ignore all the others. I only care about multiplication, that's the key operation. I only care about that. I don't care about the other declarations and stuff. Step counts. Notion of step itself is inexact. Sometimes you can call that as a simple declaration as a 0 or 1. It really depends on your view. So it's not 100% correct. So asymptotic complexity provides a meaningful statement about the time and space complexity of a program. My definition is more of a rough bound. It's not exact, but it's, at least it can provide you the rough numbers of this maximum and minimum boundary of a performance for the certain algorithms. Asymptotic complexity. And we will give you some definitions of each part. 너무 빨리 나간다. Complexity examples. Two programs have complexity Cn n squared plus C2n and Cn respectively. Well, so this is, yeah, think of it as an x squared. C1. 뭐지? C1 x squared C2x versus C3x. They like to see that two complexity. I mean, algorithm 1, algorithm 2, they have this two different complexity. I'm just using n as a x. Wow. Exactly the same thing, 그죠? If you draw that each function into graph like this. Of course, the slope will change and slightly, but still, the bottom line is this. The program with the complexity of Cn will be faster than the one with the complexity of this one, algorithm 1, for sufficiently large values of n. What does that mean? I already draw that here. Linear functions. 이거 뭐야? Linear function. It's much faster. 맞나? Yeah, linear functions will be much faster for sufficiently large values of n. What does that mean? Yeah.
When n reaches a certain large value, the second algorithm becomes more.
Yeah, how do you draw this? I'm going to pick out any point in here. This linear function is some value y1, But if I wanted to have the same number of n's, I'll be somewhere much higher than this. So this one will be faster. That's like going back to the middle school or elementary. So it's nothing new. It's just one of the applications of what you learn in the elementary schools. So what if I ask you to find the n values they meet or exceed? I mean, same thing as exceed after this point. Right? For small number of n's, either program could be faster. Depends on the value of C1, C2, and C3. These depends on what numbers that you use. If you use maybe 1000 x squared, much faster than just normal x squared. So depends on the variables. Those ratio, this meeting point will change. But if x is large enough, n is large enough, then always this statement will be true. 그죠? 뭐 여기에 무슨 값이 들어오든 간에 뭐 이렇게 되고 그런 차이는 있겠지만 결국엔 x가 커지면 윗말이 계속 맞게 되죠. So if c is 1, c2 is 2, c3 is 100, then c1 and square c2 and square c and square. Let me write it. I can't believe I'm doing this. c1 뭐야? 2x then x, this is true when x is less than 98. I'm just using x just to be familiar with you guys, but you can just switch the n, you're just dealing with this. Or if n, 98, this condition will be, so 98 might be the meeting point, exceeding point. Hopefully you can calculate this with the different values, C1, C2, C3. So you will be able to do this. Don't ask me to do this for examples. 이거 물어보면 I will kill you. 아이고 비디오 있는데. 아이고. Well, I still kill you. I don't care. Still kill you. So it's quite easy, 그죠? It's nothing much. It's nothing much. So these are the notations for the describing such cases. Asymptotic notation, I always call it as a big O. Those are the asymptotic notations if something goes extreme. Describe the behavioral time or space complexity for large instance of characteristics. At this point, we're more focusing on the time complexity. Big O notation provides the upper bound of a function f. Why do they say function f? Why go? F x function. So I'm gonna just switch. They say the function f. Omega. I don't know how to actually write it, Greeks. They come up with the very weird characters. It's difficult to write. Omega. Also a very expensive watch. 그죠? Omega. Its notation provides a lower bound. 갑자기 시계 하니까 생각나네. What is a popular brand for you guys nowadays? 시계. Did you guys see that Galaxy Gear? Anyone planning to buy that? Galaxy Gear? Or if the Apple introduced their own design, then anyone is willing to buy that watch stuff? 살 사람? 이 통사에서 공짜로 나오면 무조건 사겠지. 그죠? 보조금 받고. It's interesting. We'll see. 사는 거 나왔잖아. 뭐 이렇게 갖고. 배터리 하루가 안에 어쩌니 가는데. 그거 들여다보고 있다가 사고 날 것 같아. 그죠? Omega notation provide the lower bound, so exact opposite of the big O's. Theta notation is used when algorithm can be bounded for both from above and below by the same functions. It's a bit obscure. 그죠? Something stays much more slower boundaries. So I understand it like this. Big O, upper. Omega, minimum. Theta, right in the middle, but it's very close to the one function, right in the middle. Little o defines a loose upper bound. It's okay. Little o, I don't want you guys to know this little o. Actually, theta and little o, in terms of theta, is amortized cost. It's a very difficult concept later. I mean, it should be the 3rd or 4th year. So something in the between it should be good enough. Again, I memorized like this. Big O, omega, theta. Little o, I don't know. I don't care. I just don't even try to think about it. This is people who are studying for the algorithmic courses, time complexity stuff. I had actually one experience to work with this algorithmic research people. I went to their meetings. They actually discussed certain games. 뭐지? What is the popular board games? 뭐 옛날에 long time blue marble 뭐 이런 거 있잖아. They actually compute the time complexity of such games. About 2 hours nonstop, and they asking for a better way of measuring the time complexity of those board games. Blue marble might be one of the very easy examples, but they have certain complex. I don't know. They have their dice is 6-dimensional, whatever those games are. Actually, there are people who study that and try to come up with a better way of understanding those ideas, so they can actually conclude that this game will not finish within 100 years. Very crazy people. Very crazy people. I'm not in those areas, but people who might be interested in these areas, very, very scientific and very academic, I guess. So these are the formal definitions. I'm gonna point out the formal definitions first. 어디 갔어? Where is it? 여기 뒤에 있구나. Anyway, to the second page. Upper bound, time complexity of Tn is the function of the problem size n. We keep referring to the n. N is the one determinant of make a judgment. And the value of Tn is running time of algorithm in the worst case, upper bound, worst case. The number of steps required at most with the arbitrary inputs. Worst case of sorting algorithm, everything is mixed up. Nothing is sorted in the list. All right, then you have to change everything. What is the best case of a sorting algorithm? Everything is already sorted. You try to run a sorting algorithm on top of the array that is already sorted. Nothing to do. I mean, less comparison. You would just keep dropping out of the loops because every condition is already satisfied. Right? Worst case. Average case, the mean number of steps requires, mean is well, something between average should be okay with you. Mean number of steps required with a large number of random inputs. How do they determine the average values, mean values? For example, in sorting examples, you try with a different n's. Maybe they start with the n equal 10, and then they try n equal 1,000, n equal million, and then they come back to n equal 100. They use different n's, random orders, and then each n, they compute the number of steps. And then you add them up, divide by how many times they actually try different n's. It gives you the average values. 그렇게 하면 대충 크고 작고 막 섞어서 하다 보면 대충 값이 나오잖아요. 뭐 일반적으로 몇 개 걸릴 것 같다. 그렇게 하는데 average나 mean value를 쓰는 거예요. Examples: the sorting algorithm bubble sort has a time complexity of Tn equals to n minus n times n minus 1 divided by 2 comparison exchange step to sort a sequence of n data elements. Bubble sort, insertion sort, there are many different sorting algorithms. I'm sure the other courses will cover that. I'm not covering those stuff. But if you're interested, just type in bubble sort. There are many different animations. You can actually take a look. Different implementations too. You don't have to write it. You don't have to write your own algorithms. Already good ones out there. Often it is not necessary to know the exact value of Tn, but only upper bound of as an estimate. Like I say, rough values. I don't need to know exact comparisons of each algorithm is doing. I just need to know roughly. Maybe it was doing the 100 comparisons in average. In worst case, around is doing about 1,000. I don't need to know 1,000, 11, whatever the exact numbers. That's an upper bound as an estimate. Example, an upper bound of a time complexity of Tn of a bubble sort is a function of Fn equal to n squared divided by 2. Since Tn is Fn, Tn is less than Fn for all n's. 이거 뭔 소리야? What does that mean? What does that mean? Other values are smaller than the ones that have. That's why I usually, that's why I usually say the first part of the course, it's a formal definition of something, formal definition of big O. I usually say just memorize. Memorize. Memorize first. But things I already explained in here. They just try to write that in definition-wise. Let me just read the definitions first. Fn is equal to big O of Gn, some other values. Read as Fn is big O of Gn if and only if it can go the other way around too. I will explain. Positive constants of C and 0 exist such that Fn is less than or equal to C times Gn for all n's and is greater than or equal to n0. 이거 exactly what I said here. N goes to infinity. Certain values, the actual function values will be less than the big values, big functions, n squared. 무슨 뜻이? Even if I explain this in Korean, you will confuse. This is also what I did when I was you guys' age. When I was in university. I memorized this first. Write it down 10 times. Because I will ask you this in the questions. I would definitely ask you the definitions. Doesn't matter whether you understand or not. You will understand at the end of the course. You will understand at the end of the course anyways. So I recommend you memorize. But the thing is, whatever function that I give you, fx, I'm going to use the same notation. Fn is whatever, C1, C2, plus C3, whatever function that is, my Gn, for example this, some value C. At some point, this will be less than this one. 뭐를 해도 이거를 아무 뭐 C를 큰 걸 써도 작은 걸 써도 결국엔 n square 안에 들어간다는 얘기예요. Exact translation is this. Whatever you do, whatever C values that you do, it will be actually bounded within the n square functions. Any variation of n square functions. That's Gn. I use this n square, but you can add n to the 3, whatever, log. It's okay. Let me read it again. Fn equal to big O of Gn if and only if 아는 사람. Same thing. It's when they try to do prove something, if and only if means this condition satisfied, this is true. This condition satisfied, this is true. So you can actually prove one way and the other way always guaranteed. There are many different proofs that only have if. It means it can only goes to one direction. If you prove the second part is true, it doesn't mean the first part is true. If and only if. 근데 이거는 if and only if니까 둘 중에 하나 컨디션만 맞으면 되는 거예요. 둘 다 맞는 거예요. If and only if positive constant C and 0 exist should be something n. Fn is less than Cg of n for all n's, including n goes can be infinity, or n is greater than equal to n0. 똑같은 얘긴데 글로 써놓으니까 좀 헷갈리죠. Exact same. What might be a omega definition then? If you're giving a big O definition, what might be the omega definition? 여기서 뭐만 변하면 되겠어? Yeah. Let me quickly go to that. This is omega definition. The directions are changed. So if you memorize one definition, then you'll be okay with the rest of it. Let me read it from the beginning. The asymptotic complexity of function fn is forms an upper bound of Tn for large n and goes to infinity. In general, it's just the order of the asymptotic complexity is of interest if it's a linear, quadratic, or exponentials. Exponentials grows much larger than quadratic. Quadratic is x squared. 뭐야? quadratic 말고 또 뭐 있어? 1차, 2차, 3차, 4차, 5차. polynomials. 그죠? The order is denoted by a complexity class using a big O notations. Big O notation. Let me warn you. I'm gonna warn you many times from this. Later, if I ask you the similar questions, giving me a big O values, usually people write it this way. Oh, they all know this is linear, big O. But their answer, they usually write it like this, N. I know what you mean, but it's not correct presentation of the asymptotic complexity, 그죠? Last year, I usually mark it as okay. I give you full marks. But this year, if you don't write it this way, or some people make me confused, they're always like this. I don't know whether you mean a big O or little o. So make sure I can tell which one is which. Definition. Memorize, memorize, memorize. That is, big O of G comprises all functions of f for which there exists a constant C, a number of n0 such that fn is smaller or equal to Cgn for all n and greater than or equal to n0. It doesn't make too much time. It's same thing. In Korean, again, briefly, 뭐를 하든 뭐 x 스퀘어를 가지고 얘기한다면 x 스퀘어를 갖고 날 치든 뒤집어 엎든 뭘 하든 결국에는 x 스퀘어 2차 방정식 안에 들어온다 이런 뜻이에요. n이 변할수록 n이 뭐 어떤 값을 가져도 그러니까 이렇게 쓰겠지. 그러니까 결국에 모든 sorting function은 이거다. I can say it.
G에는 상수 C가 있어야지 그게
뭐, 예, 상수 C constant는 뭐 그냥 붙여놓은 거라고 보면 돼요. 있어야죠. 그냥 1로 해도 되죠. Constant can be anything. Okay. So from time to time, I will ask to write these definitions. Write these definitions. Big O examples. The kind complexity of Tn of a bubble sort lies within the complexity class of order n square. We all know the exact value of what was the time step for bubble sort n squared plus 3n minus 4, whatever that value is. That actually within the class of n square, big O of n square. Makes sense. 그렇죠? 아주 쉽게는 이렇게 얘기하면 돼. 그래프 모양이 변하진 않잖아. n 스퀘어 2차 방정식은 그래프는 계속 이렇게 하지. 기울기만 변하지. 모양은 어차피 이 모양을 표현하기 위해서 big O를 했다고 해도 돼요. 굳이 꼭 그렇게 기억할 필요는 없는데 그래도 좀 헷갈린다면. Order n square is a complexity class of all functions that grows at most quadratically. At most 2차. Respectively, order n is a set of all functions that grows at most linear lines. Order 1. What is order 1? Order of constants, they also say. Order 1 is a set of functions that are bounded to from above or by constant. Well, it looked like a mathematics class, don't it? No. Well, we all know now order and I don't know, order 1, order of constant. How do you draw that in here? Doesn't matter n grows infinity or not, it will always take this much steps. 좋죠. If you can only dealing with the constant time complexity algorithms, it's best. It's faster, much faster, but they never grow. 이거 어떻게 할까? How do you design this? 예를 들어 아주 농담 삼아 그냥 for loop을 돌려갖고 1부터 100까지 하는 거랑 1부터 100까지 하면 for loop이니까 리니어네, 그죠? for loop 하나니까. for loop 100번 하지 말고 같은 걸 100번을 써. 그러면 오더 100이죠. 여기 어디 있겠죠? 그죠? 그건 되게 extreme case고. Constants. Order n to the k is set of all functions that grows polynomial times. There are certain algorithms that cannot be described with the polynomial runtimes. Later they call it as NP-hard problems, NP complete problems. If you're running into any algorithms that you cannot describe into this polynomial n to the 2, n to the 3, n to the 4, then you should look away. You don't fight for those algorithms. But there are many real-world NP-hard problems, non-polynomial problems. 뭐가 있을까? What might be it? We mentioned this too last year. 뭐가 있을까? Usually the scheduling algorithms are NP-hard. It doesn't have a polynomial running time, stuff like 택배 아저씨. When they actually try to build their scheduling algorithm in the beginning, in the morning, where to go first, which one is closed. There is no algorithm to determine the best optimal solutions. That's not exactly a true statement. There is no algorithm that gives you the best solution. There are algorithms that can give you the optimal solutions. Those type of algorithms that dealing with those schedulings that cannot be described with the polynomial runtimes. 그럼 상당히 많아요. Luckily, we're not gonna discuss those algorithms in this class. I don't want to. Read examples 3.1 and 3.5. Again, very smaller examples. Probably repeating what I said in class, just in case if you missed it, then you would do. The bottom line is memorize that definition. That already guarantee you a 1 point in your midterms. 1 point in midterms. 근데 I cannot believe I said this many times last year. 근데 only 50% of you got that question right. They come up with a brand new definition of big O's and their directions are wrong. Hopefully it will not happen this year. Once lower bounds, because we spend a fair amount of time in the big O's, lower bound is a piece of cake now. Once an algorithm for solving a specific problem is found, the question arises whether it is possible to design a faster algorithms or not. For example, you have, assuming that all the sorting algorithm is n square, order of n square algorithms. and someone raised their hands, I can design a sorting algorithm of a constant, order of constants. How do you know whether that is possible or not? That is the job of this lower bound. We theoretically prove that certain algorithms cannot be lower than boundaries. For example, I think the sorting algorithm of lower bound is n log n, or n square, I forgot, n square. So you cannot design any sorting, you cannot design an algorithm is less than n square. So someone claims that they can come up with a sorting algorithm order of constant, you can say, no, that's not possible. We already have a proof that sorting algorithm must have n square minimum times, like that. So that is a job of this lower bound. So you don't waste your time. We already know there will be no constant algorithms. So why not spending your time to developing one? How can we know unless we have found such algorithm? In most cases, a lower bound for a problem can be given. A certain number of steps that every algorithm has to execute at least in order to solve a problem. The least steps that you have to do to solve a problem. Example, in order to sort an element, every algorithm at least has to take a look at every number. So it needs at least n steps. Thus, Fn n is a lower bound of sorting. What does that mean? And in order to sort a numbers, I need to take a look at each element at least once, whether I do a comparison after that or not. So they put that as a lower bound. N times must be there in order to begin, or maybe you might not be able to finish, but whether you begin your algorithms. So n here is a lower bound. For that, we use omega. 카메라가 있으니까 은근히 농담을 못 하겠네. 은근히 신경 씁니다. 원래 쓸데없는 얘기도 좀 하는데, 그죠? 많이 하는데. 또 이상한 뻘소리 했다가 잡혀갈까 봐. 이미 잡혀갔겠죠. 오메가. Again, the only order of a lower bound is considered, namely if it's a linear, quadratic, exponential, or some other functions. This order is given by function class using omega notations. Definition: Fn equals to omega of g of gn if positive constants c and n0 exist such that Fn is greater than or equal to c times gn for all n's. That is, omega g comprises all functions of f for which there exists a constant c and number of n0 such that the Fn is greater than or equal to c of gn for all n of g. And for all n, it's okay. N can be equal or greater than n0. I can also draw. This is not a good example. Linear might not be good. Let's say this is n squared. Some other n squared values, I don't know, C1. Let's say somewhere here. Let's imagine that lower bound is below this. If you want to remember this way, it's also okay too. Big O, omega n. It's not correct, but you should be close. Space in between. This is how much room that you have. 이거는 뭐 좀 다른 얘기인데 나중에 theta. Almost close to the 1. But it's difficult to tell which one is theta, which one is not. Just by definition wise like that. So if you have a difficulty of understanding the definition in text, picture this in your brain. Hopefully it'll help you to understand a bit better. So same type of question can be asked, right? What is the value of n of the when you're comparing two different functions? What is the meeting point? Let fn 2 times n squared plus 7n minus 10 gn equals n squared. Since we see, since width c equal 1 for all, for n equal to n0, 1, 2, we have 2 to the n, 2 times n squared plus 7n minus 10, blah, 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 c, and c times n squared. Thus, fn is omega g. 몰라, I don't care what they say. I don't care what they say. It's okay. You don't have to understand at this point. This example function fn lies in omega n squared. That's the important part. Whatever they do, they come up with this. Bottom line is this. They juggle around. So you can say it lies under a omega n squared, as well as order n squared too. It grows at least quadratically, but almost at most quadratically. It's both. Omega and big O is n squared, same. In this case, you can actually say that theta is also n squared. 그렇죠? Maximum이랑 minimum이랑 is same. So why not? Depends on the theta definitions. Theta definition right here. Right in the between. If you combine the big O, small O, not small O, I'm sorry. Omega in the between theta definition. That stays in between the upper and lower bound. Let me go back to the previous one. At least quadratically, at most quadratically. Omega n squared, big O n squared. In order to express the exact order of a function of the class theta f is introduced. Theta. Omega example 3.6, read it, but probably the same. I forget whether we have a similar picture in the textbook. I think we do. Sometimes I get a question that my example here is different from the textbook. Of course it's different. Numbers will be different. So I don't think I'm saying anything wrong, but just simply different examples. Okay. I say this because many people send me their emails asking why your example is so different from the textbook. But it's basically the same thing, different numbers. Okay. Another definition to memorize, but once you have a big O definition memorized, it's a piece of cake now. Theta used when a function of f can be bounded both from above and below by the same function of g. Same thing. I should draw this bit there. Well, now it's bounded onto this part. Definition: if n theta g of n, read fn is that theta of g of n if and only if positive constant c, c1, c2, and 0 exist such that they stay in the between. They stay in the between. Then you can call it as a theta of n. Again, I'm going to just read it. That is, fn lies between c1 times the function of g and 읽기도 귀찮다 이제. c2 times the function g, except possibly when n is smaller than n0. Same thing, what I explained here. Seeing that above the lower bound for the sorting problem lies omega of n, it is upper bound lies in the big O of n squared. Using bubble sort, how can the gap between these two functions can be bridged? Is it possible to find the tighter lower bounds or tighter upper bounds? Yes, it is possible to sort faster, namely in times of n log n. n log n, big O of n log n is faster than n square. 그죠? n log n is faster than n square. So it says there are faster algorithms for sorting bubble sort, which can be done in n log n times. With the heap sort, the lower bound can be improved the omega of n times log n. Heap sort is optimal sorting algorithm since its upper bound matches the lower bound for a sorting problem. Blah, blah, blah. We can continue this next class. We give you a bit more examples like this table looking. We'll give you a bit more clear pictures on that part. Again, I have a list of people here, but I only have 46, so it doesn't mean anything that I called you names today. 그 출석 체크하면 좋은데 나 지금 시스템에 46명밖에 안 올라와 있어서 아마 수요일 날쯤이나 돼야지 다 올라올 거가 봐. 그때 마저 다 부를게요. Any questions today?